So, hello everybody. Well, here it's well, for me it's a pity not to be possible to be there with you. As you know, I love. Well, some of your teachers know that I love Finland and Lahti, and unfortunately, the two last editions I was not able to go there to the International Week, and this year is going to be online, which is a pity. Okay, so I'm JordiLinares. I'm a teacher, a professor, and also a researcher in the Polytechnic University of Valencia in the campus of Alcoy. We have a very important relationship with your university, with lab, okay, now for many years, and now we have a couple of double degrees, one of them in computer science, okay? Okay, so my objective is very difficult, okay? So because to introduce something such as artificial intelligence, machine learning, and deep learning is really, really hard. And it is really hard in 3 hours, okay? It's so I don't know if I haven't, well, I don't know. I will try to adapt the pace of the presentation depending on the time, okay? Because it's very difficult, okay? Because there are many concepts and many things. But at least my idea is to try to give you an overview of what is going on, you know, because I'm sure that you are detecting that for the last 10 years, something is going on, okay? There's a hype in the artificial intelligence field, and there's a reason because of this hype. And I'm going to try to explain to you why, okay? And well, to give you a bit of an idea. So I'm JordiLinares, as I'm saying you. So as a matter of fact, my PhD, when I studied, the computer science degree was a 5-year degree. So in order to do my PhD, it was not necessary to do a master because we have 5 years already. So we had to do 30 extra credits, and I did them in the artificial intelligence program. Okay, so my PhD is basically focused on that. But after that, I have to say that last year I really finished another Master of Science in Artificial Intelligence, because after almost 20 years from my PhD, the things have changed a little. So I had to be forced somehow to renew my knowledge in the field, because even right now I'm tutoring a couple of PhD theses in this field. So it's important for me to be up to date to this interesting world. Okay. Okay, so intelligence. Okay, so as you can see, we are going to be talking about artificial intelligence and intelligence. So as you can see in this slide, it is even difficult to define intelligence. There's no agreed upon definition about intelligence. This is really funny, but nobody has a definition of intelligence. Okay, many people agree that two very important characteristics of intelligence is to be autonomous and adaptive, okay, to new problems and situations, okay. And well, in living organisms, okay, in order to be autonomous and adaptive, it's clear that data in general has a very important role. As we are going to see, this is going to be also the case in artificial intelligence, okay? So, this is something interesting. This is something interesting because, you know, we are going to be talking about artificial intelligence, and imagine that instead of that, we are going to be talking about aeronautics, okay? And you are trying to compare one plane with another, okay? Imagine that you don't have a way to measure how good or efficient this plane is regarding the other one, okay? This is exactly the situation we have in artificial intelligence right now. There's no way now, formal way, to measure intelligence and, in consequence, to measure artificial intelligence. So this is a problem, okay? Because we are talking about if machines are or not intelligent, but we don't have any kind of formal mechanism to measure how intelligent something is, okay? So there are very interesting papers, this is very recent, on the measure of intelligence. And as a matter of fact, we have, I have a colleague of mine in my department, Jose Hernandez Orallo. He also works in the University of Cambridge. And he has a book talking about that when we talk about intelligence and, of course, artificial intelligence, we are talking about, or we are focusing the problem from an anthropocentric point of view. So with the human being in the middle, it's like talking about aeronautics. We compare the new plane we are making in Boeing regarding to a bird, okay? And the bird is the element we have to compare with. No, we have physics, okay, in order to know, to measure the qualities or the performance of a new airplane, okay? And this is something we still don't have in artificial intelligence. This is a book of my colleague of mine, where they are trying to create this way of measuring intelligence in general, because as you can see here, the intelligent landscape is really big, and the human intelligence is just part of it. Inside what we call natural intelligence, okay? But there are some animals that they have superior cognitive properties than the human beings, okay, in different areas. So of course, we think that we are, and we are, of course, the most intelligent living forms in the earth in many cognitive areas, in the main cognitive areas, but not in all, okay? So this is a problem, okay? We have always an anthropocentric vision of this thing, and they are people working, trying to remove the human from the equation, okay, about intelligence. As you can see, artificial intelligence is growing up, okay? So now there are things the computers can do much better than we do, okay? And it is growing up, okay? It's growing up, and little by little, okay, is possible to do more and more things using artificial intelligence, okay? So there's no definition about artificial intelligence, no standard definition about artificial intelligence. So here you have several of them. The study of how to make computers do things at which at the moment people are better. This is something we really do in our research lab, okay? In our research labs, normally we are focusing on that, okay? To try to put the computers into the limit, okay? Something was not possible to be solved before, let's try to solve it now using a computer. So maybe this is the, maybe, as you can see, there are many definitions of artificial intelligence, but there's no definition of intelligence. So it's difficult to define artificial intelligence and to have a unique definition, okay? So it's almost up to you, okay? Here you have the different areas of artificial intelligence, because artificial intelligence is a very big area, okay? We started talking about artificial intelligence about the middle of the last century, okay? I think it was in 1956 or something like that, when the artificial intelligence term was coined, okay? And here you can see more or less a diagram of the different areas, okay? Not necessarily chronological areas, but some of the areas we cover when we talk about artificial intelligence, okay? So intuition, searching, advanced searching, I will try to describe that better, swarm intelligence, evolutionary algorithms, genetic algorithms. And recently, we are, the hype, of course, of the artificial intelligence come from machine learning, which is nothing new at all. But 10 years ago, something changed. And is now the reason because we have this hype, okay? In particular, artificial neural networks, okay, which is going to be part of the main part of my talk, maybe an important part of it, okay? Okay, so see the different areas, okay? And you can see even books and articles and journals focused on every single point of these different areas, okay? So it's a very huge, huge, huge area, the artificial intelligence, okay? What is now a hype, as I'm telling you, we have an explosion, okay, is when we talk about machine learning, okay? And we will see if this machine learning approach, especially working with deep learning, we will see if this is going to somehow invade or cover, okay, all the different approaches we have, all the other techniques we are using in artificial intelligence, okay? But here you have the symbolic approach, which was the traditional way to work with artificial intelligence, the genetic algorithms, and well, the multi-agent systems. I will talk a bit later, okay? So this is just to show you a little diagram of some of the different areas, a kind of mind map, okay, we can say that, okay, of the different areas we can have when we talk artificial intelligence. And as you can see, it's really huge, okay? It's a very huge area with many people in the academia world and in companies working in different problems, okay? So it is absolutely impossible that someone could be able to control and to know and to master just one of these areas, okay? It's huge, okay? Really huge. But what we all agree about intelligence, okay, when we talk about intelligence, is that somehow is related with perception, okay? To interpret and interact with what we are perceiving, okay? This is something important in intelligence. The ability to search for the best solution and solve problems, okay? This is very related with reasoning and planning, okay? And another feature very important in intelligence is learning and adaptation. So that's very important, okay? This autonomous and adaptive vision I was talking about, okay? But also, and many researchers are working quite a lot on that, creativity, emotions, social skills. So that's also important because, as you know, even when we talk about intelligence in humans, and the emotional intelligence, the social intelligence is something we talk about, okay? So we have, of course, to try to explore the possibilities we have in artificial intelligence in this area, okay? So this is some of the elements of artificial intelligence following what it is called the see, think, act paradigm. So again, something related with perception, machine learning, to be able to represent knowledge, okay? So to be able to learn and somehow these things you're learning must be stored in the model, this knowledge. We must be able to reason, okay? So maybe using logic, okay? And using inference rules, we have to be able to create, okay, a new knowledge, new insights. We have to be able to plan, okay? If the problem is complex, to create this plan, okay? To act, of course, and well, there are some of the main characteristics when we talk about an artificial intelligence system. When we talk about artificial intelligence, many people are relating that also with data science. It's not exactly the same thing, as you can see in this diagram. They have a very big intersection right now. But in data science, we have extra things regarding statistical analysis, exploratory analysis, and so on. When we talk about artificial intelligence, we can be talking about heuristic search, for example, that is not related with data science. But of course, we have an intersection. There's a nightmare right now with artificial intelligence, data science, big data, data analysis, many cognitive computation. So many of these terms sometimes are used because marketing reasons, okay? So, well, but they are different, okay? And we have to be quite strict defining them sometimes, okay? So traditionally, the main areas in artificial intelligence, when I was studying in the beginning of the century, artificial intelligence, we were working a lot with that to try to get the knowledge of an expert, okay? And to put this knowledge somehow in the computer using graphs, using ontologies, and then to use logic, okay? And the traditional logic rules in order to inference, okay, new facts, okay, and to be able to reach a goal or a decision, okay, working with that, okay. This is still valid, okay. There are still people working in this area. Artificial intelligence is also related, and I will talk about that also later, not only when the problem is complex, okay? So artificial intelligence is not, of course, is when we have a hard problem, okay? But sometimes the problem maybe is not hard. Maybe the problem is very simple, but the inconvenient is the space search. For example, this is this game where you have where you have a picture and you can move one of the blocks. There's one missing, and you have to start moving the blocks, you know, in order to rebuild the original picture, something like that, no? So if we want to solve that using a computer, or we want to solve tic-tac-toe, for example, we can find the optimal solution during executing what we call brute force, okay? So we study all the combinations and we select the optimal one, okay? But is that possible in chess? No way. So what happens there? What happens there is that we have to use what we call heuristic search. So we have to work with this tree, okay, of possibilities, but we have to decide what branches of this tree we are going to be working with in a specific time and discard others, okay? So we need to have a kind of criteria in order to know from a specific node, okay, if this node is interesting or not. So it was really difficult sometimes to find this function, this heuristic function, okay? And somehow we are providing some kind of intelligence because we are not able to explore all the possibilities, and we have to help the system to look for not necessarily the optimal solution, but a solution, okay? And not to be forever, okay, looking for the optimal solution, okay? This is planning and scheduling, okay? It is based on the previous problem. Again, we have to see all the combinations, okay? We have to explore all the combinations. Some problems, we can explore all the combinations and to find the optimal solutions, and others, we have to use heuristics again, and we have to find maybe a solution, suboptimal solution, not the optimal one, but because the search space is so high that we cannot explore all the combinations, okay? And machine learning, of course, I'm not going to give you now too many information about that, but of course, machine learning is going to help us, as we are going to see, to let the computer to learn, okay? Based on examples. This is basically the idea, and we have different families. Pattern recognition. This is very frustrating for some of my colleagues. I have some colleagues that they have been working for 10, 20 years in computer vision, applying very sophisticated techniques in order to identify objects and so on, okay? And with the explosion of deep learning, as we are going to see, these old feature-based approaches are old. So all the papers and theses and works they have done, they have been improved and quite a lot using the new techniques we have in deep learning, okay? Natural language processing, natural language understanding, in these areas, many very interesting things are happening, okay? We will see some examples. Okay, so deep learning, okay, we are going to be talking about deep learning and why this deep learning thing is something we must know. I have to tell you something. In next month, I'm going to start with a new course in our university in the degree of computer science, where I'm going to be teaching machine learning and deep learning. I think that in 2, 3 years, 4 years, if you don't teach in a university these areas, you're going to be in trouble, okay? Because as you are going to see, this is growing up very quickly, and the kind of solutions we can have are incredible. And the market needs professionals, okay, able to understand these techniques and to use these techniques, okay? So I will talk about this deep learning thing and some information about this deep learning consequences, okay? So deep learning, okay? Especially supervised deep learning is the one with better results. I will describe you also reinforcement learning a bit, that it is also having very important breakthroughs recently, okay? Many very interesting things happened last year, not only COVID, okay? Many interesting things happened last year, okay? So we will see some examples, okay? And you will see that deep learning is going to be a reality now in 2021 because we have big data, a lot of data. We have big models and very powerful models. And we have computational power. Okay, this is the trinity. Okay, without these three elements, there's no hype in artificial intelligence, machine learning, deep learning. Okay, we need these three things, and it was necessary to have the three things. Okay, now we have them. Okay, so this is why the hype, as we are going to see. Artificial intelligence, as I'm telling you, works with hard problems, okay? So we put ourselves in the limit. What is the kind of thing a human being is able to do now that cannot be solved using a computer? This is our horizon, okay? But sometimes we can have a solution to a problem, but it's a not affordable solution. Okay, for example, chess. Okay, chess. Can we solve chess? Yes, we can. In 100 lines of Python, you can create a program in chess that is going to solve chess. It's going to explore every single possibility in front of a white move. What is the possible black move, and what is the possible white moves, and so on. So we can create this huge tree of possibilities. 100 lines of code in Python. What is the problem? You have here the problem, no? The problem is time and even memory in order to solve this problem, okay? So brute force is no solution, okay? There's no atoms in the universe to solve these problems, okay? So we need, of course, to do something. And also when we are working with not theoretically hard problems, but problems with large search spaces is where we have to solve them using artificial intelligence, as we human beings do, okay? Because a chess master, of course, does not explore every single possibility when she is playing, okay? So something is happening in his brain or her brain in order to make a right decision in the time they have during the match, okay? So we have to do something similar, and this is the reason because artificial intelligence also works with large search space problems, okay? So it's clear that we have had several breakthroughs. We are going to talk about them, but at the beginning, these breakthroughs have been, let's say, how to say it, amazing, but interesting, but not able to solve anything really dramatic for the human being and the society, okay? So for example, to beat Kasparov or to beat, I don't remember the name of the South Korean man that was defeated playing Go. Well, this is interesting, but well, the society, the human society, okay, fantastic, but nothing changes, okay? But you have to see that these breakthroughs, sooner or later, they go to the scientific world and they are applied to solve problems that they really change what, how our life is and is going to be, okay? So we are starting to have some real consequences of the application of these artificial intelligence breakthroughs, okay? We have had situations, terrible situations, or rumors about the possibility of changing elections. But anyway, personal assistants are becoming a reality. Autonomous cars are starting to work. As you know, in order to detect cancer, skin cancer, and these kind of things, we are having very good results, and working with X-ray images, we are even going beyond what an expert is able to do. So when we talk about breakthroughs, okay, normally we start experimenting with, let's say, games or stupid things sometimes. But the good point is that sooner or later, we are applying, or some people are applying that to real problems, okay? So in artificial intelligence, I like to say that we have the good, the bad, and the ugly, okay? In this world, okay? The good are, of course, the academic people, the researchers, so we are very good, okay? So young and bright, okay? Well, young and bright in my case, well, young and bright, okay. Well, in the limit, no? But it's true that there's a lot of good talent, okay, right now. And the things are evolving very fast because there are very young people with very good ideas and a lot of stamina in the academic world, okay, the good thing. The bad are, of course, you know, you have Google, Amazon, Microsoft, Facebook. The bad guy in the film is those that are using these techniques in order, of course, to get profits, okay? And the ugly, of course, are even when when this gives superpowers to nations or to people that maybe are not the right ones in order to decide, okay, what is good or what it is not good, no? Fortunately, we don't have Trump anymore, but I cannot imagine Trump giving his opinion about ethics and things like that regarding artificial intelligence, okay? So it's good to have some decisions in hands of people with, let's say, a little of brain, okay? Or Putin, oh my God. Okay, so this is part of what we are living, is part of the fourth industrial revolution, okay? We are talking about artificial intelligence, big data, Internet of Things, cloud computing, and so on. So, of course, this is changing many things in the industry. And if I have time, I will show you an example on how we, in our lab, we are using artificial intelligence and deep learning in the field of the industry, okay? A very interesting application. Well, this is what the people now, when talking about artificial intelligence, the people more or less agree in these three types, okay? Again, the problem is that they are very anthropocentric again, okay? So I'm not very happy with this division, but more or less, this is how we divide currently artificial intelligence, okay? It's anthropocentric because, again, the human is in the middle, okay? And this is sooner or later, we need to remove the human component here in intelligence. But what we have now, that we call it narrow or weak artificial intelligence, this is what we have now. Very powerful artificial intelligence solutions that can be better than human beings.
No joo, me ollaan Patrikin kanssa jo eilen viimeksi oltiin tuossa siis sulla on otettu tausta ja teollisuudessa toistakin vuotta. Ja...
Matti, sulla on mikki päällä.
Okay. So narrow or weak artificial intelligence, okay? This is what we have now. Narrow and weak, pay attention to that. This means that narrow means that they are very specific, okay? Maybe we have something that it is incredible, but focused to a very specific problem. But we can have even better results than the human beings, okay? For example, we have now systems that are better in diagnostic activities than specialists, doctor specialists, okay? The problem, when we say narrow, is because they are not flexible. We cannot get this system as it is and to put it into another environment, okay, and to expect good results. No, we have to create very specific solutions to specific problems. So far, okay, so far, okay. General or strong AI is the people, when talking about general artificial intelligence, normally they say, well, when the machines have the same cognitive possibilities that a human being. Again, this is problematic, okay, because we cannot measure very well what intelligence is, okay, so it's going to be problematic. In some areas, computers are already better than we are, okay? And I don't know if we are going, this is not going to be a clear line, okay, where we say, voila, we have the general artificial intelligence. No, this is going to be a gray, okay, transition, okay, towards cognitive capabilities that are unique right now, so far, to the human being. And then we can talk about super artificial intelligence, which means that we can go beyond the human beings, okay? And well, we can talk about that later, okay? So artificial general intelligence, a machine that does tasks it has never seen and has not been prepared for beforehand. This definition, I like it, okay? As you can see, it's not anthropocentric, okay? I like it much more. So general artificial intelligence means that you have something that it can be very good solving something, and if you change the environment and the rules, this model is able to adapt, and it is able to learn, and it is able to provide solutions without any further intervention. This is maybe the definition I'm much more comfortable with about artificial general intelligence, okay? So traditionally, we have had two schools in artificial intelligence, okay? We have had, well, the one I was trained when I was in the university and in my PhD studies, okay? The symbolic artificial intelligence, which means that basically we get the knowledge of an expert, and then using logic or using other kind of inference mechanisms to generate new insights, new knowledge, okay? And there were people think that with that, we can solve everything, okay? And that was not true, okay? It was proof that only with the symbolic approach, we are not going for sure to beat human beings in some specific areas, okay? So this is also called the good old-fashioned artificial intelligence, okay? Right now, we have, again, what we call the connectionism, which means deep learning, which means neural networks, okay? Chronologically speaking, we started with that, okay? But we haven't had good results till recently, okay? This is another way of solving the problems, okay? So somehow some biology inspiration, okay, in the neurons, okay? So till now, the symbolic artificial intelligence has been good for this kind of problems you have there. Reasoning, game theory, automatic planning, optimization, and so on. And so far, using neural networks, we are very good right now using for machine learning problems, okay? Computer vision, robotics, these kinds of things, okay? The thing is that, as I'm telling you, the artificial neural networks, okay, ANN, they started very, very soon, okay? Look the dates, okay? So it was something old. But so at the beginning, it was, from the beginning, there were people that they saw that this approach had a lot of advantages and possibilities. But the problem is that overall computers and computer power was not enough in order to work efficiently with that, okay? So very soon we started only working with the symbolic artificial intelligence, okay? So the symbolic artificial intelligence, it has been the normal artificial intelligence we have had for many years, okay, many years. This is the thing I studied when I was in the university, and basically what I studied when I was studying my PhD, okay, 20 years ago, okay. So here you can see a chronology, okay. Pay attention overall to what we have in the bottom, okay. As you can see in the 50s, okay, we are working basically thinking that neurons, in that case were perceptrons, okay, was a good idea, okay, to have this connectionism, something I'm going to describe. But the lack of computer power, okay, basically, and other techniques made that the symbolic artificial intelligence became much more important, okay, much more important. But now, okay, again, okay, connectionism again, okay, with deep learning, okay. We have had winters, okay. Winters in artificial intelligence are periods where we were very sad, okay. We say we are not going to be able to create an intelligent machine with the cognitive possibilities of a human being, okay. So we had at least a couple of winters, okay, where the people, the researchers, they were very pessimistic, okay. Now it seems that we are in a kind of spring, okay, or summer, or perpetual spring, okay. I don't know, but if we are going to have another winter in the future, it is still far away, okay. So the possibilities of deep learning, as we are going to see, are we are far from taking the most of them, okay. So there are still a lot to do, okay, and many good breakthroughs for sure we are going to have in the future. What is going to happen is going to be enough, I don't know, in order to make something equivalent to a human being, I don't know. But this winter or future winter is far away, if there is a winter, okay, in artificial intelligence again. So right now, the top-down, the symbolic approach, they normally work with knowledge we put somehow from an expert. And the other approach, okay, using neural networks, what we do is to work with data, okay, not knowledge. And to create knowledge from data. You know the difference? The difference is quite different, okay? The symbolic The professional is the one that puts the knowledge, okay? As we are going to see in deep learning, what we put is data, and we are expecting the system to get the knowledge, okay, from the data, okay? It's quite different. Now we have hybrid solutions, okay? Something, things in between, okay? But the bottom-up, the connectionism techniques, the neural networks, the deep learning is growing. So let's see what is going to happen finally to the symbolic traditional artificial intelligence. There's maybe you can see also you can see people talking about artificial intelligence agents and multi-agents, okay? The things are very complex, you know, in artificial intelligence. Even if you talk about an autonomous car, in an autonomous car, you don't have a unique artificial intelligence system. As a matter of fact, you have a collection, large collection of elements, some based on symbolic artificial intelligence, other based on deep learning, and they all are working together, okay? So we talk about multi-agents, okay? So it's a nightmare because how you finally decide something, how you make a decision, okay? So there are different artificial intelligence agents, okay? And finally, they are transmitting information between them, and somehow you have to make a decision. The car has to stop, or the car has to turn to the right or to the left, okay? So this is very interesting, okay? The artificial intelligence agents and the multi-agents, okay? When we have different elements, okay? Somehow working together, okay? Solving a very complex problem, okay? So as I was telling you, okay, the exit, sorry, the exit, the success, okay, this is my Spanish. The success of the current artificial intelligence is based on three things, okay? Data, okay? Models, very powerful models, okay? And power, computing power and storage, okay? These three things, okay? We need three things, okay? Data, computing powers, and very powerful learning models. Without the three, there's no hype, okay? And this is why this hype started in, as we are going to see, in 2012, okay? 2012 is a very important year for those of us who work in computer in artificial intelligence. I'm going to tell you why. So data. More data was created in the last 2 years than the previous 5,000 years of humanity. Okay, so data, if it is for data, okay, oh my God, okay, so data is very important. And the thing we have now is, thanks to internet and so on, we have a lot of data, okay? So that's a very incredible advantage, as you are going to see for deep learning, okay? Computing power. As you know, we have this famous Moore law, okay, where somehow every more or less a couple of years, okay, depending on what aspect about hardware or components you are talking about, but every 2 years, more or less, we are somehow doubling, okay, the performance somehow, okay? It's true that from 2015, there are people doubting about the Moore's law, but there's very interesting things in the horizon, you know. We are talking about, of course, optical and quantum computing, carbon-based or graphene-based computing. So there are some breakthroughs, okay, in the future that can make even this evolution much more important, okay? So this is the Moore's law, as you know. So it has been very important till 2012, okay, in order to have what we are going to be talking about, deep learning and the success of deep learning, okay? So we need power. And GPUs have been very important, okay, for this moment we are living now. We have now TPUs, okay, which are devices much more specialized than the GPUs in order to work with deep learning, okay? But just with the GPUs, we are right now able to do very incredible things, okay? Also, it's clear that we have to take into account something very important, okay? The energy consumption, the carbon print, okay? So maybe you are listening that this artificial intelligence thing is consuming a lot of energy, okay? So it's important also the efficiency, okay? So the engineers, of course, they are also taking that into account, okay? We cannot use normal CPUs. We need to have much more specialized devices with less power consumption and much more specific, okay, to work with deep learning and artificial intelligence. And learning models, I'm going to talk about that a lot, okay? I'm going to try to skip maths as much as I can. But with the deep neural networks, okay, the connectionism is back, and the models we can create with deep neural networks are incredible right now. Okay, we can create very sophisticated architectures right now, able to do very interesting things, okay? And we will talk about that, okay? So this is the global scope of artificial intelligence, okay, where we have inside machine learning. In machine learning, we have a lot of techniques, and inside machine learning, the revolution, the deep learning, okay? The one everybody is talking about, okay? But don't forget that there are other areas outside deep learning with which we can solve real problems. So it is not necessary, okay, to be using deep learning, okay, when we work in artificial intelligence, although it's true that deep learning is behind this hype, okay, this beautiful, let's say, moment we are living right now in artificial intelligence. Here, another chart where we can distinguish a bit a lot of these topics that sometimes overall in the press, okay, in the news, you can see a bit of nightmare, okay? No, artificial intelligence is something very specific, machine learning, deep learning. Big data, some people talk about big data as artificial intelligence. No, big data is big data. And we have problems in big data that nothing related with artificial intelligence, okay? We have to work with structured and non-structured data, and we have to think on how we can manage that. And we are not talking about artificial intelligence at all, okay? So of course, there's an intersection, okay? As we have an intersection with data science and data analytics, okay? So this is the normal, okay, way also to see that, okay? If you want to see it as these Russian dolls, okay? It's another alternative. What it is true is that right now in 2021, when we talk about artificial intelligence, we are normally working in one of these areas, okay? Recognition computer vision or recognition of voice recognition or something like that. Human conversation and human interaction. To be able to predict, okay, things in the future, prediction, okay. Goal-driving systems, okay, when you are maybe trying to plan something, okay. Autonomous systems, example given a car, an autonomous car. To look for patterns or anomalies, this is also very interesting to detect, for example, that the lab website is trying to be hacked, okay? We can use artificial intelligence techniques in order to detect something that is an anomaly and maybe are related with something dangerous, okay? And of course, hyper-personalization, okay? We want, of course, to make the machines and devices, smartphones, and so on, to be highly personalized to our profile. And we want them to, in the future to make them intelligent. So if I need extra help in something, give me this extra help. If I don't need it, don't give it to me, but in an intelligent way, okay? So we don't want to be saying, show me this, show me that. No, I want the system to be able to personalize automatically, intelligently to my profile, following my actions, okay, with the system. So deep learning is becoming, and we are going to talk about that, is becoming a revolution, okay, in many areas, in computer vision, in speech recognition, natural language processing, language translation, time series prediction, pattern recognition, okay, a lot. Recommendation system, of course, Netflix, Spotify, the recommendation system are working very well, okay? So talking about artificial intelligence, as we are going to see, we have machine learning, and then we will be talking about something called representation learning, and inside that, deep learning, okay? And I will give you what is the difference between machine learning and the traditional machine learning techniques and the deep learning that belongs to the representation learning, okay? Achievements, okay? This slide was till 2018, you see? And you can see here some very interesting achievements, okay? Breakthroughs, okay? Incredible breakthroughs, okay? And we stop in 2018, okay? Talking about AlphaZero's victory against Stockfish. Stockfish was the most powerful chess program, okay, till this moment. And the people from DeepMind, that belongs to Google, using AlphaZero, what was based on AlphaGo, using reinforcement learning, they were able to beat Stockfish, okay? Right now, we have the people from DeepMind, they have a system better than this AlphaZero of the 2018. And even Magnus Carlsen, the chess master, okay, the #1 in the world, the way he's playing right now, and I know that very well because my son plays chess, the way he's playing now is influenced by AlphaZero. Okay, so somehow we are going beyond, okay, the new systems are being even creative, okay, in the methodologies and strategies in order to play chess in this context, okay? So there's a lot of difference between AlphaZeros and Deep Blue, the one that beat Kasparov, okay? The Deep Blue was Symbolic AI. AlphaZero is deep reinforcement learning. Okay, the approach is totally different. Okay, totally different. Okay, to the same problem. Okay, 2018, but look, 2019, 2020. Okay, for example, you can see now news like this. This is DALI. Okay, DALI. DALI is a system created by OpenAI. Now there's a competition between DeepMind and OpenAI. OpenAI, you theoretically speaking, you put a text, okay, describing something, and it is able to generate, okay, images like this. So for example, if you say, I want an armchair with the shape of an avocado, okay, this is what you get, okay? So, wow, this is still a prototype, but the consequences of that in the designing field is going to be very interesting. Then you have Clip, okay? OpenAI Clip is able to do something different, okay? It's also based into GPT-3, which is, I don't know if you're familiar with it, look for it in internet. It's based on something called a transformer with more than 17 billion of parameters in the neural network, so it's really huge. And it has been trained with almost all available information in internet or useful information in internet. And it is able to do very incredible things, okay? It is able to create articles, okay, that look like totally human, just with some initial sentences, okay? Based on that, OpenAI Clip is able to do something similar, okay? But then you have Mu0, okay? DeepMind's Mu0. This is incredible, Mu0, okay? Mu0 is the evolution of AlphaZero. In AlphaZero, the people that define the AlphaZero system indicated to the computer the rules of chess, the pawn, the movement of the pawn, or the knight, or the bishop. So the rules of the chess were given to AlphaZero, okay? In a first version, the openings, the database of openings were also introduced in the system. And they discovered that using this human information was not a good idea. So they decided just to use the rules of chess. Okay, with Mu0, not even that. The only information the system has is when a movement is legal or not, and if you have win or even the match. Nothing else. No information. So Mu0 is a revolution because it's the first deep learning architecture that without rules and in a totally dynamic and unknown environment, just by try and error, is able to understand the game, learn how to play the game, and finally beat the opponent, okay? So this technology, when this technology is applied, is going to be applied to problems we have in science, this is going to be incredible. Because this narrow artificial intelligence is going to be less narrow, okay? So it's a very good movement towards artificial general intelligence, okay? There are some people, they are Spanish people, as a matter of fact. This is something I'm going to show you later, that they are proving formally that if we are able to create a super artificial intelligence, they are proving mathematically that we will not be able to control it. Okay, I will show you that later. Okay. So I don't know if you follow these things, but there has been also a very important breakthrough from DeepMind. So till now, DeepMind was beating players in chess, in Go, perfect. Okay, but what? What is the benefit of this technology to the society, to the human beings? Okay, so the people of DeepMind, they started to participate into a contest, okay, a kind of competition, trying to predict the 3D shape of a protein using the chain of amino acids. A problem that for 50 years, nobody has been able to solve. And if we want to know the three-dimensional shape of a protein, we can need even 1 year of research, $150,000, and very sophisticated machines in order to know what is the three-dimensional shape of this protein. With the three-dimensional shape of this protein, we can do incredible things in medicine, okay, and in biology in general. AlphaFold, and particularly AlphaFold 2, has achieved, this was by the end of last year, has achieved much more precision, accuracy, than even using the best machines in order to predict using real amino acids, the 21 amino acids, the shape of a protein in 3D. So now the pharmaceutical companies, they have done something like, what? So for the very first time, DeepMind has proved that they are not playing, that the solutions they are creating using deep learning, and in this case, deep reinforcement learning, they can make a very incredible difference, okay? A very incredible difference in the medicine. So many things are not going to be tested into a normal laboratory, but in a computer, okay? So maybe in the future, a vaccine is not going to be necessary to be, even in a record time, 1 year in the COVID case, maybe we will be able to deal with this kind of problems using computers only, okay? So pay attention to that, okay? So artificial intelligence is being used right now to predict in dangerous mutations, to diagnose, for diagnosing cancer using the urine, a lot of things, okay? So when we talk about artificial intelligence, don't only think about technology, okay? We live in a human society, so we have to talk about legal and regulatory framework. We have to talk about ethics. It's problematic in Europe. For example, in China, is the government, the one is controlling everything, and in United States, the companies. In Europe, we like to put that into the European Union, no? And somehow, when we talk about things like ethics, privacy, and things like that, everything is understandable, of course. But when we mix that with healthcare, you know, and you say that if we get the information of the healthcare of everybody with this data, we can produce incredible drugs and medicines. Oh, okay, there's a lot to talk about that, okay? And of course, we have to be very careful with that. Very, very careful. But I'm sure China is not going to be paying attention to that. So we cannot also lose the competition, okay? So we have to, I don't know, to compete somehow. We have to talk also about people and society, and of course the economy and the consequences this new technology is going to have, of course, in the economy and in the labor market, for sure, okay? So we have some limitations, and the limitations, the problem with the limitations, you know, don't trust anybody that it is not involved in the field of artificial intelligence, okay? If you read something about that artificial intelligence or deep learning is not able to do this or that, and this one is a journalist or someone that comes from philosophy world or whatever, don't pay too much attention. In this group, I put Mark Zuckerberg and Elon Musk, okay? For me, it's the same thing. Only pay attention to people like Jeffrey Hinton, Jan LeCun, Geoffrey Benjo, Goodfellow, and even them, okay, what they say sometimes, and they say that openly, sometimes they make mistakes in their predictions, okay? So it's, okay? So some of the limitations we have today are limitations we have today. Okay, let's see what happens. But it is true that there's a problem with bias, okay? But it's not a problem of artificial intelligence, it's a problem of data, okay? Lack of veracity, of course, with now you cannot trust anything, okay? Believe me, with GPT-3, you can create hundreds of tweets, articles with very well written, okay? Able to convince anybody about anything, okay? Even you can create fake videos, fake images, so you cannot trust anything right now, okay? The problem, I'm sorry guys to tell you, okay, the problem is that I'm sure that you see this artificial intelligence, machine language, learning and data science, and you say, wow. But look at the man blocking you saying, oh, mathematical and statistical skills. That's true, okay? I don't want to lie to you, okay? That's true. So sometimes we want to jump directly to deep learning, and in the middle, there are many steps, many steps, believe me, that after having a PhD in the field, I finished last year a Master of Science in Artificial Intelligence, and I was studying during 2 years a lot of maths again, okay, and I'm in my 50s. It was very terrible, but it's necessary. It's necessary because if not, you can do a lot of things. Believe me, you can do a lot of things. But when you are playing with something that is a kind of black box and do magical things, when you have problems, maybe you don't know why, and you don't know what to change in order to solve it, okay? But if you have the mathematical background, you are, of course, in a better position in order to solve these kind of problems, okay? So theoretically speaking, all of this is required, okay? So, wow. So, wow. As I have to say that in Spain, in our university, we have created a new degree only focused on this, okay? So, data science degree only, okay? Only for that, okay? For me, I don't know. if it is a good idea or not. The best man I have met, and the one I ask whenever I have problems, is a guy, he's in his 30s, and he has a double degree in maths and computer science, and a master's degree in artificial intelligence in Stanford. Okay, so this is this is for me the perfect combination. Okay, so here you have some well, look, minimally required subjects for working with artificial intelligence. Well, if you want to be a professional, okay, but I don't want to discourage you. One thing is that if you want to become a professional in artificial intelligence, machine learning, and deep learning. Another thing is that you're in a company and maybe you need a solution where it could be interesting to have something related with machine learning or deep learning. Believe me, it is going to be easier than you expect, because there are a lot of startups and frameworks that are going to help you in order to create layers that are going to allow you to use incredible things without knowing a shit about deep learning. The problem is that they do what they do. Whenever you want to do something different, maybe, of course, because you don't have knowledge, you cannot change the model, or you cannot do anything different, okay? But anyway, there are many problems right now we can solve without knowing anything about deep learning, thanks to startups and frameworks, okay? This is a flowchart I like from Karen Howe. She's from the MIT, because it's really funny, because right now, everything is artificial intelligence, okay? There's no company, okay, without the word artificial intelligence. Even our politicians, okay, it seems that they have artificial intelligence flowing from the ears. I don't know. No. As you can see, this flow chart says, can it see? Yes. Can it identify what it sees? Yes. Cool. Is using computer vision and image processing. Is artificial intelligence. If not, it's just a camera. And the same thing with hear, read, move, and reason, okay? Not everything is artificial intelligence, okay? I like this flowchart because, well, this is a meme, okay? We use machine learning algorithms to greet the user with a personalized message, okay? Give me the name, hello, and your name. Now, it's obvious that not everything is artificial intelligence, and not everything is a chain of if statements. Is not artificial intelligence. It has to be dynamic, okay? Even when we use symbolic artificial intelligence, we have something similar to these ifs, but they are not codified, okay? It's something you have a knowledge and you have rules that are triggered, okay? So you don't have a, let's say, a traditional structure, okay? Okay, so artificial intelligence is likely to be either the best or the worst thing to happen to humanity. Okay. Look, I was talking about, these are Spanish colleagues from a university in Madrid. The article is from the beginning of this month, okay, in the Journal of Artificial Intelligence Research, and one of the most important journals. And they prove formally, using maths, not just speculating, no, using computing theory, okay, formally, okay, they proved that if we have a super intelligent, we won't be able to control it, okay? This doesn't mean that we are going to have Terminator, okay? Is meaning that maybe we have to pay attention to some elements in artificial intelligence, okay? So again, only pay attention to the godfathers of the artificial intelligence, like Geoffrey Hinton. The other man is Demis Hassabis. He is the leader of DeepMind, okay? And you can see that sometimes they say things that they seem contradictory, no? Artificial general intelligence is nowhere close to being a reality, okay? And in the other hand, it says, deep learning is going to be able to do everything. It seems incompatible. It is not. We are talking just about time and breakthroughs, okay? This is Geoffrey Hinton has an article, very nice article, and he says that artificial general intelligence is possible, but it's possible we need time and also some additional breakthroughs, okay? New things. Are you familiar with singularity? Okay, if not, read about singularity, okay? Because singularity says that if we are able to create something really intelligent, even more intelligent than human beings, with this computer program, software, whatever, we can create another one even better, and another one even better, and another one even better. So we are going to have not an exponential growth, no, a hyper exponential growth. We are going to have a singularity, okay? And the man that it is talking a lot about that is Ray Kurzweil, okay? The book is from 2004, if I'm not wrong. It's interesting to read it, okay? It's interesting to read it. And he says that the singularity is near, okay? He's very optimistic, okay, about the consequences. But without any doubt, it's interesting to see the opinion of this man when humans transcend biology, okay? What can happen, okay? Okay, so with that, we have this, with this first part, okay? The introductory part of artificial intelligence, the general one. But I would like to go to the two specific topics, okay? To talk about machine learning first, okay? Machine learning, and I'm going to be talking about the classical techniques of machine learning, okay? So let's try to understand machine learning first. And after that, and I think, I hope we are going to have time, okay? After that, okay, we are going to be talking about deep learning, okay? Which is the thing I'm much more interested in showing you, okay? So what is machine learning? Okay, here you have a definition: field of study that gives computers the ability to learn without being explicitly programmed, okay? Tom Mitchell did a much more formal definition of that, but this is the idea, okay? The idea is, okay, I want the computer to learn something, okay? And this something is complex. It has to be complex. If it is not complex, oh my God, you are learning Python, C# or whatever, no? No, it has to be complex, okay? And the only solution to learn that something is by learning. Learning, what it means to learn. Learn means that normally we see examples and we learn from these examples, okay? So mathematically speaking, we can see it as this formula, very simple formula, okay? where X is the data, okay? And what we want to calculate is Y, okay? So the data, okay, is whatever, features, we say, okay, characteristics, okay? And we want, okay, that the algorithm is going to be able to give me a result, okay? So what do we want to do in machine learning? To estimate this function f. So if we have a collection of examples where we say, for example, this man, okay, or this person is a man, 50, diabetes, cholesterol, or whatever. And this man, unfortunately, has died because of COVID. Another person with these features, alive. Another person with these features, dead. Another person with these features, alive. Can we relate these features with the fact that if it is alive or dead? Can we predict? Okay, first, can we learn? After that, can we predict? Okay, this is the idea of machine learning.
Sorry to interrupt you, Jordi, but what about the break?
Yeah, do you think how much?
What about 50 minutes? Is it
15?
15, yeah.
Okay, that's perfect.
Okay, is it perfect to you? So if we continue to, okay, 15 to 3.
Okay. Okay, perfect.
Okay, so I will.
Okay, don't worry, don't worry. Okay, so let's go.
Yes, go.
Let's go. So
let's go. Yes.
I'm going to pay attention from time to time to the chat, okay? The problem is that if I put the chat visible in my screen, I don't see the slides. But from time to time, I'm going to see it. Very nice questions, okay? I agree with many of what you are saying, okay? And if you want, I can, when I finish, to add something, okay? But yeah, very, very interesting. You're understanding me, which is something good. Okay, so where we were talking about machine learning. Do you remember? So how can we make a machine to learn? Okay, let's go quickly, okay? Well, we have been doing that for many years, almost from the beginning of the maths, okay? This is called, for example, linear regression, okay? So if you have something like this, where the X, okay, is, for example, how tall you are, and the Y is your weight, okay? So maybe you can have a chart maybe like this, I don't know. So you can try to find a line, okay? This function can be just a line in order to more or less, okay, learn from the amount of data you provide to the system, okay? This is called linear regression. And of course, is generally useless, okay? Because it is very limited, okay? And this is problematic, okay? But it's just to show you that machine learning, it doesn't mean something very, very, very complex, okay? It can be something very simple. Okay, so what we have in traditional programming, okay? You are developers, okay? And what you do normally, okay? You're in front of Eclipse or you're in front of Visual Studio Code and you say, okay, this is the program, the rules, okay? And then you run the program and the user introduces the data, okay? And the program runs, okay, and provides answers, okay? But now with machine learning, no, the idea is different. The idea is we have data with the answers. And what we want to get are the rules. Do you understand? So I want to say, a person that goes to the hospital with this symptom, this symptom, this symptom, this symptom, this symptom, and finally lives. Another one, this, and finally die. This, and finally lives. What I want to know is if I have 1 million, well, 1 million, well, 1 million is perfect, of these cases, if I can introduce them, can I get the rules? Okay, so now if someone else comes into the hospital and I can see the data, okay, can I get exactly what is going to happen? In another way, traditional algorithm, okay, logic, the program and the input, and you have the output. What we are going to do in machine learning is now, we are going to provide input and output. I mean, the data of the person and what has happened with him, her, okay? And training with an algorithm, we have a logic, we have a model, we have the rules, but we don't have generated the rules programming, okay? Now someone comes to the hospital, we see the features, we call it the vector of features, okay? The data, the symptoms, the elements, the age, or whatever, and we try to predict what is going to happen. Following the model, we have get from the training process, okay? Very different, okay? So this means that, for example, in traditional programming, in order to distinguish what you are doing, you have to create the rules, okay, and program the rules. So if you have a new case, okay, your program, you have to modify the program. Your program is not able to react properly to a new situation. Why? Because the program is the program, okay? So using this if-else structure, fixed structure, we don't have enough. Symbolic artificial intelligence was much more flexible, okay, with this if-else, okay? It was able to work with predicates, okay, that triggers depending on facts. But anyway, okay, we, even with symbolic artificial intelligence, we were quite limited. The idea now is get data that defines that someone is walking, running, going in bicycle or playing golf or whatever, okay? And put to this data a label, okay? In the case of supervised learning, as we are going to see, okay? And train the system, okay? With a lot of data, a lot of examples of walking, running, going in bicycle, a lot of them, with the label, in the case of supervised learning, as we are going to see. And then, if something new comes, okay, we are able to distinguish which one it is. But what happens if we want now to detect that it is playing golf? Well, it's going to be very dynamic. It's not going to be dramatic. It's just to add a new category and to train again. The only thing we need is the data to play golf, okay? So this is the concept of machine learning, okay? When we use machine learning, no, not always. The task is too hard to be programmed, okay? It's also something interesting when we have a large search space problem, chess, for example, when adaptivity is essential, and of course, when you have the data. No data, no machine learning. So the success of the new artificial intelligence is because you have data. No data, bad data, unbalanced data, biased data, you have a problem. Okay. So sometimes it says, okay, GPT-3 is biased against Muslim people. No, GPT-3 is not biased. The data used to train GPT-3 was biased. Okay. So the algorithms are pure and beautiful. Okay. The problem comes from the data side, okay, where we have to pay attention to. So machine learning is a family of algorithms and techniques where we try to learn automatically from this data, okay? So we want to generalize behavior, okay, from this data. So this means that what we are interested in is with new elements to try to predict, okay? This is the objective, okay? And we have three main families: supervised, unsupervised, and reinforcement learning, which is normally the one you like the most, but it is also the most difficult to understand mathematically. Ugh, it's a nightmare, okay? In supervised learning, we have fantastic results, and it is very simple. Is what I'm saying to you. Someone goes to the hospital with symptoms, and finally it happens something to him or her, okay? So we have a large collection of people with symptoms and what has happened with them. We have a label, okay? If we train the system using this information, this is supervised learning, okay? And supervised learning is, we have just the data. We don't have labels. So we want an algorithm able to take in this data to look for hidden patterns or structures or anomalies or groups. We call them also clustering, okay? Are we able to analyze in this data that to see that this data, as a matter of fact, is grouped somehow, okay? This is unsupervised learning. And reinforcement learning, the algorithm try out lots of different things and is rewarded or penalized depending on whether its behavior help or hinder it from reaching its objective, alpha zero. This is why alpha zero was playing against itself millions of matches, okay, millions. Because in order to get what we call the policy, okay, the strategy the machine uses in order to make a movement, in order to train this policy, which is something complex, it needs to try different alternatives and to receive a reward. And this reward is going to be back propagated to somehow to the previous decisions, attenuated, okay? And in this way, playing a lot, okay? Finally, internally, we create some kind of n-dimensional matrix of weights, okay? With the strategy, okay, that tells us in front of a specific movement what to do, okay? It's based generally in an algorithm is called Q-learning, okay? And this algorithm is very well known. And what DeepMind is working now is with deep Q-learning, okay? I will try to show you later. Then we have outlier detection, okay, that can use supervised and unsupervised. We can have semi-supervised techniques. Now is a fashion to talk about self-supervised. In this area, we are entering into meta-learning, okay, trying to see if we can solve the problem we have right now. You know, we have a problem where we are achieving very good results, okay, but we need a lot of data okay? A lot of data, okay? But in the other side, a 3-year-old boy or girl with less data is able to reach a very good accuracy as well. No? So we need a lot of data. Why so need of data? Okay. So self-supervised techniques are trying to relax this situation. As a matter of fact, it's not fair to compare a human being and an algorithm, because even a 3-year boy or girl, his or her eyes are activated during 16 hours per day and processing a lot of information during 3 years. So it's a bit unfair to compare them, okay? Well, in self-supervised learning, the people is trying to make the neural networks, as we are going to see, much more flexible, okay, in how we can generalize, okay, the knowledge, okay. So this is the traditional 4 families of learning, okay. The one that gives better results is supervised learning, and reinforcement learning, thanks to DeepMind. Wow, we are having very incredible results. AlphaFold 2, okay, the algorithm I was talking about for the protein, there are people that they are saying that it is worth a Nobel Prize because it's a problem of 50 years trying to solve this problem, okay? So, and the consequences of that are going to be incredible. So in supervised learning, this means that we need data and label, okay? Data and label, data and label. And then we are able to predict, okay? We can classify when this label is a category, or we can make regression with this label is a numeric value. For example, if you know the square meters of the house, where it is the house, how many floors has the house, this is the price, okay? So if I give you a lot of examples and I give you a new house, can you predict the price? This is regression because it's not a category. What you are predicting is a number, okay? The unsupervised learning is trying to do what you have, what you have here in the bottom, okay? Clustering, okay? Trying to look for structures, patterns, anomalies, okay? There are no labels, okay? There are no labels, okay? And it is much more complex to get results, okay? Semi-supervised is sometimes we have a lot of elements with labels, but much more without labels. Can we make the most of the ones without the labels to help us somehow? Yes, there are techniques that using a mixture between supervised and unsupervised, they can improve what the result we could get only using supervised. So this extra information, even without labels, can help us, okay? Depending on the context, okay? Again, I like the flow chart of this woman, Karen Howe from the MIT, okay? When to use machine learning, okay? When to use machine learning, okay? Are you looking for patterns in massive amounts of data? Yes, machine learning. Is it being taught what to look for? Yes. Telltale sign is supervised learning. So for sure it's supervised learning. No. We need to find the solution by trying and error? Yes. Reinforcement learning? No. Supervised learning. So are you using deep neural networks? So then, that's very funny, take the technique and put the prefix deep, okay? If not, it's very boring, okay? You cannot add the adjective deep to your technique, okay? So I like this flowchart. So this is supervised learning, as I'm telling you, okay? We can classify and we can make also regression, okay? So in classification, okay, we have labels with the data. With regression, we have numbers. We train, and then we want to predict the label in classification or the value, okay, in regression, okay? So training and prediction, two very important stages. Training, of course, is going to be much more time consuming. It means that we have to fit the model with data. And with this data, the model, the algorithm, has to generate the model. We are going to use afterwards for predicting, okay? This is the idea, okay? The prediction generally is faster, okay? Once we have the model trained, the prediction is faster, okay? And the prediction means that a new element comes and we have to know what happens, okay? The problem here is that this machine learning thing is challenging, okay? It seems that, oh, we don't have to program anymore. That's quite relaxing. Now the problem comes from the side of the data. So still the professionals, we have to think again, oh, terrible. Why? Because what are the features we have to get from the data in order to train the model? What are the important elements, the important characteristics? Is it the age, talking about COVID? Is it the symptoms? Is it where she lives? Is it the color of the hair? What are the features? Okay, so the features are not easy to get, and the results are going to be very different depending on this. So this is why this is called feature engineering, because this means that any change in the features means that you have to retrain the model again, okay, because you can get different results. So the prediction means that we have to do exactly the same to get the subject, to extract the features, okay, and using the model, okay, we have created in the training stage and to predict what happens, okay. So the things are becoming difficult here. Some of my students, they say, oh, we don't have to program. This is going to be funny. No, it isn't, because we have to work with the data. So we need to do this exploratory data analysis. So before selecting the features, we have to visualize it. We have to process them. We have to wrangling them, which means that we have to adapt the features in terms we can work with in the algorithms. We have to sometimes scale them. Sometimes we have to work with missing values. What happens if with a specific subject, we don't know if it has diabetes or not? What we do with this subject? We say that it has diabetes or overweight. We don't know that. What we put? We have to put something. If not, we cannot predict, we cannot train. So there are many problems, okay? Many problems. And also another problem is the curse of dimensionality. The more features, the worst results we can get in our prediction. Okay, this is terrible as well. In the classical techniques, in the classical machine learning techniques. Here you have an example of exploratory data analysis and using Python, NumPy library, Matplotlib, Seaborn, pandas. Using the collection of tools we have, and they are open source, we can easily analyze this information before training our model. So for example, we can have this correlation matrix where we can see if two features are very similar. They are somehow correlated, and this is dangerous. It's dangerous, or at least we can remove one. In this case, residual sugar seems to be very correlated with density. So maybe we can remove density or residual sugar, okay? So we have less variables in our model, okay? The metrics, that's very important. Well, we train the model and what? Now we have to measure the model, how good the model is, okay? And what we do, okay? What we do? Well, you're going to see it clear here. What we do is, this is the data, no? So what we do is, for example, we get the 80% for training the model, okay? Then with this 80%, we can predict what happens with the model with this 80%. The model not necessarily is going to give you 100%, okay? It depends on the model and how many data, okay? But you can get a metric of accuracy with the training. But is that a good idea? Well, to get more or less an intuition is okay, but it's much better that we predict with the 20% we haven't used in order to train the model and to see the error there, okay, of the model. This is going to be statistically much more valid, okay? This is what this slide is indicating, okay? Why we don't use the 100%? Because we can have a very terrible problem in machine learning. It is called overfitting. Some machine learning techniques, they are so good that they learn by heart the data. So they give you 100% with the training data. But then you try to predict a new element and it fails. Wow. So in order to avoid that, we need to use this technique, okay? We need to be sure that our model learns from the data, but without losing generalization. So it cannot, this is a balance, this is a trade-off. You cannot, the model cannot learn every single detail of the data, just the general essential of the data, okay? And that's really difficult, okay? So difficult that even we use cross-validation, okay? We repeat this, for example, 80-20, okay? We repeat it several times, okay? And we make the average, okay? So we train with 80, we test with 20, then we select another 20%, we train with the other, and so on, okay? So it's a nightmare. And this is one of the reasons, because when you train, you need a lot of computational power, because internally, you're retraining the model a lot of times, okay? A lot of times. Okay, you have here another slide talking about that, okay? This is a nightmare. The good point, okay, is that if we have time, I will show you. If you work with Python, NumPy, Pandas, scikit-learn, TensorFlow, Keras, PyTorch, and these tools, these libraries, of course, you are going to have libraries, tools for making this task affordable, okay? So this is what we are going to fight, okay? This is our fighting battle. This is our battle every day when we work with deep learning, which is an iterative process, okay? The training is iterative. using back propagation. We need to train the model, but to stop, okay, in order to avoid overfitting, which means that the model is giving us better and better results with the training data set, but it starts to give us bad results in the test data set. That's not good. We have to stop and to find this trade-off, okay? So we want the model to learn from the data, but not too much, okay? Because we want the model to be general for future elements, okay? So we don't want to have a table, okay? This input, this output. No, we want to get the essential from the data, the essential thing. This is unsupervised learning, okay? And we normally use a technique, very famous, it is called K-means, okay? Or hierarchical methods, okay, to work with that, in order to look for hidden patterns, okay, there, okay? It is a clustering technique. There are no labels, okay? So we need just to try to find patterns, okay, with this information. This is very useful for anomaly detection, okay? This is very useful now, even for fraud detection, okay? And attacks, for example, to your servers, okay? To detect these anomaly behaviors can be essential in order to see that maybe you are being attacked or something like that, okay? Okay, so reinforcement learning, which is normally the thing you like the most, the problem is that it is mathematically, if we can, I will show you a slide, mathematically is difficult, but the idea is that you have an agent, okay, that it is in the middle of an environment and has no idea what to do, what action to do, okay? So using try and error, okay, and chooses, and finally wins or loses. So it has a reward or a penalization. And this reward and penalization somehow is going to fit in a back way, okay, all the previous decisions with a factor that makes this to be dumped, okay? So finally, you create what we call a policy. And the policy is a model that is going to help you what to do in the future, okay? In front of a specific environment and an action to carry out. And this is why one of the chat questions is not only interesting to put two machine program, chess programs fighting each other, it's absolutely necessary in reinforcement learning, okay? Absolutely. All in reinforcement learning means that it has been trained against itself, okay? In order to find this policy, okay, that allows the system to beat the human and beats the human in many cases, okay? Okay, so if you want to study data science, this is all the process, okay? Exploratory data analysis, to clean the data, to generate the models, and then to put it in production, okay? And if you want to put it in production and you use Python, you can use Flask, for example, or Fast APA, or Streamlit. They are libraries that allows you to put your model in a website, okay, in a server. So in production, let's say, okay. So Python is one of the advantages it has, okay. I like Python. The other programming language many people is using is R, but Python has much more advantages because you can make web services totally in Python and a lot of more things in Python, not only artificial intelligence, okay? So here you have some of the areas where we can use these three main techniques, okay? Recommender system, for example, is a clustering technique, of course, okay? So they try to group the clients somehow, okay? Because when you are using Spotify, from the very beginning, you don't say what are the things you like, no? It analyzes your choices, and then it has a vector of features of you, and then it can use this vector in order to use an unsupervised learning technique in order to see in what group you match, okay? So you like, I don't know, classical music and reggaeton, okay? Very curious combination, okay? So this is the kind of techniques recommender system are using, okay? Unsupervised learning, clustering. So I have to say that next February in Alcoy, where you have a double degree in computer science, you can come, okay? We have, as a matter of fact, 5 students, our student there, and I want to have someone from you here, okay? Well, this is the techniques I'm going to teach my students next month, okay? Some of them, okay? And of course, we are going to finish with deep learning, which is normally the first thing you want to do, okay? But no, we have to go step by step, okay? So as a matter of fact, see, using, for example, a very popular library, scikit-learn in Python, you have more or less a cheat sheet telling you more or less what library or sub-library to use depending on your problem. As a matter of fact, there are, in this chart, there are more than 60 different machine learning algorithms. It's a nightmare, okay? So you need something to decide, okay? And there are a lot of information depending on your problem, okay? The accuracy is one of the most important things. Obviously, accuracy is very important, okay? So you are looking for accuracy, okay? But what happens with, for example, interpretability, also called explainability? What happens if you go to a bank and you ask for a mortgage, and the banker says to you no, and you ask, no? No. Why? And the banker says, no idea, because I'm using a deep learning algorithm with your data, and the deep learning neural networks, okay, they are black boxes. So I have no idea why the system has decided that you don't deserve a mortgage. So maybe in a bank, it's not a good idea to use deep learning. Maybe it's much more idea to use something with less accuracy, but with much more facility to explain to the client why a decision was made, no? So accuracy, interpretability is something very important right now in some areas, okay? And unfortunately, deep neural networks are #1 in accuracy, but it's the area where we have more problems in order to understand why a neural network makes a decision, okay? So even the people of DeepMind, they didn't know why playing Go or chess, the system decided to do one move or another, okay? It's millions and millions and millions of parameters related with the millions of neurons, okay? So it's even divided by layers and so on, is very difficult to know exactly the reason that the system has decided in order to make a decision, okay? Another thing to take into account Okay, another thing to take into account is the amount of data you need. Okay, take into account that if you want to use deep learning with a good accuracy, the amount of data you need is much higher. Okay, much higher. Okay, you need the more data you have, the better your neural network is going to work. So elements to take into account when selecting methods, if you can explain what this algorithm has made a decision or not, if it can work with all the information in the memory or not, the number of features, if it needs or not a good balances between the classes, this is important. If it can work with categorical and numerical features, if the data is linear or not, many things. This prediction and training speed. So this is why in the real world, look, these are some of the roles you can have in a company, okay? Theoretically speaking, what happens normally is that you are going to do everything. This is very similar to when I teach game development, no? Where you explain in a game company, you can have these roles. And you visit a company and everybody has to do almost everything, no? Here we have something very, very similar, okay? The good point is that we have many, many tools, okay? So Jordi, you are scaring us, maths and techniques and methods, don't worry, okay? If you want to become a machine learning professional, no doubt, you need probably a master's degree, okay? Specific in this area, okay? That's true. This is what I did. But if you need to just make use of these techniques, to solve a specific problem, maybe you are lucky. And there are, as you can see, and this is for sure going to change, hundreds of startups, frameworks, and tools you can use in order to help you. Okay, maybe some of them without having too much knowledge about what you are really doing internally. Okay, so well, that's also something you have to take into account. Okay, so techniques, linear regression. This is the very basic technique. Logistic regression, we use a function, it is called sigmoid. Okay, it's an exponential, it's based on exponential function, 1 divided an exponential, okay? And it is very good for many problems. We can use also the famous bias theorem and the naive Bayes technique, okay? We can use decision trees, So this technique we have used many times in order to solve problems, where we say, it's a kind of questionnaire, no? You ask sex, male, here, female, here, age, here, there, and depending on that, you decide, What decision trees, the technique in machine learning, what we try to do is that these decisions of these nodes, okay, are based on mathematical concepts and things like entropy and things like that, okay? So it's not an arbitrary decision. It is to be able to create that, okay, using maths and using a formal methodology, okay, in order to create these decision trees. As a matter of fact, a very famous technique right now is random forest, that what they do is instead of creating one unique tree, they create a lot of trees, okay? And then they use all of them in order to average the result or to select the category with the majority of votes, okay? And this seems to get better result than just using a unique decision tree, Okay. We can use geometric tools. This is the supported vector machine. Okay, they were very famous before the deep learning. Okay, and here you can see a real example. Okay, very quickly by a colleague, Victor van Hoel, and the objective was to detect the probability of death. Okay, in front of a COVID patient. Okay. So it is very nice because this example, because you face the problems you can have. Where you can collect the data. You need individual data. The aggregated information you see in the news is useless. Of course, it has to be anonymous, okay? What features to select? Victor has a lot of problems on that, okay? So finally, he detected a very well-known database in Mexico City, okay? And he was using this information, okay? Taking into account that aggregated information is useless, okay? So using this SINAVE database from Mexico, okay, he was able to use clinical, social, and demographic data, okay? And to use also a large collection of features, age, diseases, sex, symptoms, demography, social environment, and so on. So he had to deal also with overfitting, and he used cross-validation to validate the models. He has a problem with unbalanced classes, so you have to be sure that when training the model, 50% of the people finally dead and 50% finally recovered. If not, the models, okay, they have a natural tendency towards the class with more data, okay? Missing values. He has problems also to decide what to do if you don't know if it's overweight or not, the man or the woman, okay? So he made some decisions. And after that, using libraries in Python that automatically, believe me, make many of these things, okay? He was able to see what machine learning models were the ones with more accuracy, okay? And even he was able to fine-tune the models using hyperparameters, okay, to work with some parameters of these models, okay? And finally, that's very interesting, he decided to select logistic regression, which is the second in the ranking. Why? Interpretability. Because linear regression is easy to see why someone or what variables or features are the ones that are more likely to produce you death or recovery, you see, which is what you have here, okay? So interpretability is also important, okay? Maybe here we could use deep learning, but maybe, okay, with that, we were not able to see what variables, okay, were the what features were the most critical ones. He even was able to make a compact model, okay, with only 6 features, okay, with a great degree of accuracy, okay. So is Victor happy? No, he is not happy. Why? Is this method going to work in LACTI? The information we get from Mexico is going to be good in LACTI. We have to check it out. We cannot say yes or not. My impression is not. Why? Because Mexico City and DF, 20 or 30 million people. So they live in flats, very little spaces, a lot of social interaction. I think you Finnish people, you are not very famous for social activities, no? Well, it's a joke. But this means that a model, okay, that works well in a place, maybe it's a disaster in another place, okay? So terrible. So this is a very good sentence. Essentially, all models are wrong, okay? But some are useful, okay? So that's very, very true, okay? That's very true when we talk about machine learning, okay? And to evaluate the errors or our models is a nightmare. Is where we start working with maths, okay? Fortunately, these packages we have in Python, they do this task for us without problems, okay? But if you pay attention, these are parameters, we are talking about the tests about COVID, okay? Specificity, sensitivity, okay? So what we are using, okay, here is becoming famous, unfortunately, okay? When we are evaluating the quality, okay, of the model of the test, sorry, we are using in order to detect if you have COVID or not. Okay, so finally, and very quickly, finally, what you were expecting, okay? The most interesting maybe part, okay? The deep learning thing, okay? So we have seen some classical machine learning methods. What makes deep learning special, okay? What makes deep learning a special model, training model? Let's see. The special thing, as you are going to see, is that it is inside something we call representation learning. And that's, you're going to see, very incredible. So what's that? What's that? Okay, let's go directly to the point. Okay? Victor and the work of the COVID, okay, he was making feature engineering. He was trying to select what features, symptoms and things were important or not, and retraining the model and so far. Feature engineering is terrible, okay? And we have been using it even in computer vision for many years. In computer vision, in front of a X-ray picture, we were using feature engineering. We were trying to detect the edges of the tumor, the density or the size or statistical parameters like the mean, the standard deviation. So feature extraction from even an image was a nightmare, okay? And there are hundreds of articles in international journals talking about that. So we, the human, we were in charge of that, okay? And it was terrible, okay? What we try with representation learning to work with the raw data. So an image, not to pre-process the image and try to get the edges of the image to convert it into grayscale, to try to morphologically do this, erosion, dilation, dilatation, and some, no. The image, okay? And let the algorithm that creates the model to automatically select the features, to learn what features from the image are essential. So, from in traditional machine learning, someone like Victor, the example I have given to you, where you were extracting the features manually and thinking, in deep learning, we have the opportunity as a representation learning technique to use the raw data, images, video, audio, okay? No pre-processing even, okay? How is that possible? Okay, let's see. Another example. Traditional machine learning using a decision tree, okay, generated with a machine learning algorithm, deep learning. No feature extraction. So here, well, I'm not going to lose too much time, but here are the differences between traditional techniques or all machine learning techniques and only deep learning, okay, only deep learning. But let's go to the point, okay? How we can solve this problem, okay? Well, again, remember that we are trying to estimate a function, okay? A function that from a set of features, okay, we try to predict something, okay? The problem is that instead of many traditional machine learning techniques that this function is unique, what we are going to do is the connectionist approach, is to create little units, okay, able to solve a very simple calculation, but to connect them in a network and trying to see if with this approach, we are able to solve complex problems, okay? Yes, we are. As a matter of fact, what happens in deep learning is that we do this. And what happens is that from a very something complex input, which it can be an image, is complex, okay? Each step, okay, each step, if these nodes are divided into layers, are getting much more simple concepts till finally you're able to detect if it is the traditional example, a cat or a dog, okay? So this started a long time ago, okay? Look the dates, okay? But we didn't have the computational power. So why we are using that? Thanks to these people, okay? Basically, in 2006, these people, they were awarded with the Turing Award, okay, which is the Nobel Prize, okay? These people, they were able to take, again, the concept of perceptron, neuron, and to improve the training process, the backpropagation algorithm, and also to be very clever in how to train, okay, them and to use the GPUs of a computer in order to make this possible, okay? And everything, the explosion is 2012 with AlexNet. So 8 years ago or 9 years ago, okay? So thank you to this improvement in the techniques that we have now more data than ever. And now we have very powerful machines. We have the success of deep learning. And see, this is very interesting. This is the ImageNet contest with 14 million images, okay? And 20,000 hand annotated categories, okay? Supervised learning, okay? See what happens in 2011, 25.8 error. Look what happens in 2012, 16.4, okay? AlexNet. From this moment on, all the academic world said, sorry. And look what happens the next year, and the next year, and the next year. Look, 2017, 2.3 error. The humans make more errors classifying the images. In front of an image, there are humans doubting if it is a bus or a truck. And maybe the neural network is able to achieve much more accuracy, okay, in this decision. Why? Because the deep neural network is able to see relationships, patterns in the information no human being is able to see. Even the most expert in X-ray images of something can skip some relationships that a big neural network can get. Okay, that's the point. Of course, we depend about the data again. Okay, so this is the AlexNet. Okay, that uses this specific kind of neural network. It is called convolutional neural network. Okay, and from 2012, a hype. Okay, since then, computer vision. I have colleagues of mine that are depressed. All his life, their life invested in publishing articles in international journals, thinking about future engineering and methods, and now a silly convolutional neural network is able to get much more accuracy. Oh, dramatic. Speech recognition, reinforcement learning. In this case, we call it deep reinforcement learning, okay? Natural language processing and so on, okay? Here you have the neuron. You see, the neuron is something very basic, okay? It's an entity, okay? It doesn't exist, it's not tangible, of course. Where we have inputs, the A's, A1, A2, the inputs. Then we have a weight, okay? We multiply the input by the weight. We sum them all, okay? We add B, which is a bias, okay, a constant value. And then we apply a very simple function. It's very simple function. And we get a result. You see? What is our mission? To train the neuron, okay? So if the A's are the input features, you see, let's see what we get as the output. Compare the output with the label of the data. So we have what we call a loss function or a cost function, no? An error function. And depending on that, what we do? Retrain the neuron. How? Modifying the weights. The thing we are going to be doing is to modify the weights, okay? And the bias, okay? So we train this neuron with a lot of information. We calculate the error, and using maths, we modify the weights, okay? Finally, okay, we will be able to train the neuron. The problem is that with just one neuron, we have just only linear classification. Nothing interesting. Nothing interesting. So in the neuron, this function you have here, traditionally we have used this, the sigmoid function, okay? Now we use it only in the last layer, okay? It's mathematically is difficult to explain why, but we don't use it anymore inside the neural network, okay? But this is what we do. Instead of having only one neuron, we have a collection of them, okay? And traditionally, not necessarily, what we do is to organize them as you have in this diagram by layers, fully connected, okay, and feed forward, which means that the information goes from the input layer towards the output layer. No information back, okay? There are exceptions. recurrent neural networks, okay? There are exceptions, okay? But this is the classical diagram of a neural network. So this is what we call the feed-forward network, okay? Okay. So in the input layer, the image, you see the pixels of the image. In the hidden layers, internal layers, neurons, and in the output layer, it depends on what you want to do. If you want regression, normally you are going to have only one neuron with a value, or you are going to have a collection of neurons if you want to get a class, a category, okay? So here, using this algorithm that it is called backpropagation, okay, we try to fit the neural network, for example, with an image to calculate what is the result. As we are using supervised learning, the difference is the error, okay? And we try to propagate, okay, using maths, this error backwards, okay, modifying the weights of every single neuron, okay? The more examples you give to the neural network, the better result you are going to have, okay? It's difficult, okay? It's inspired in biology, yes, but only because we have inputs and an output. Stop, okay? The similarities end here, okay? It's not nothing to see with a real neuron in your brain, okay? It's just a mathematical function, very simple, okay? So here you have a diagram of what happens, okay? Once the neural network has been trained, of course, okay? If you have trained the neural network, okay, which means that you are introducing a lot of examples, you get a result, and you penalize, you transmit this difference between what you get and the reality to all the weights of all the neurons. Once you have done that, you have a result like this, okay? Well, this is not exactly what we do with images, because here we are working with one-dimensional array. That's not true. We use convolutional neural networks, where we work with the spatial relationships, okay? But even using one-dimensional array, all the pixels in one column, believe me, you can get I was able to get 85% of accuracy using this data set, okay? I'm going to skip this part, okay, very quickly, of course, okay, because we are finishing. But as I showed you in one of the slides, if you want to understand neural networks, you need to understand the backpropagation algorithm. And this means that you need to understand how you calculate this cost function you have to minimize, okay? And the difficulties we have in order to do that. We cannot do that analytically. We have to use an algorithm. It is called gradient descent, okay? Which means that you have to look for the minimum of this cost function, the minimum of the error, iteratively, step by step, okay? This is why when you train a neural network, you do it using batches, and every collection of batches creates what we call an epoch, okay? So it takes a lot, okay? And we are moving, okay, this, we have to touch every single weight and every single bias of all the neurons. So this is why we also use stochastic gradient descent. So we even make a statistical approximation. So we don't use all the examples all the time in order to calculate the gradients, okay? The direction where this ball, okay, where this error has to go is based on the concept of gradient. Do you remember derivatives? Do you remember that the derivative of a function is the tangent? So you are following the tangent, okay, trying to find the minimum. The thing is that you have no security that you are going to find the minimum, because normally this is not the shape. The shape is very difficult, very complex. And this is the shape with two parameters. In a neural network, we have millions. So we are talking about the hyperspace, okay, with a lot of minimums, okay? So it is very likely, no, it's improbable that you are going to find the minimum. But that's not a problem, because the minimum could be overfitting. It could be when you have learned too much from the examples. Okay, so this is why this stochastic gradient descent strategic works. Okay, using this back propagation algorithm. Okay, this is not the end of the story, and my students have to see that we have other activation functions. So sigmoid is not used now. We use normally ReLU. We use also regularization techniques, okay, in order to penalize the neural network and to force the neural network to be general, okay? So we want the neural network to be general, never to learn too much from the examples, okay? And this means that we use a lot of techniques. Even deactivation, the dropout, is while we are training the neural network, we deactivate some neurons, okay? From sample to sample, from data to data, in order to make future co-adapting. So every neuron learns a bit of everything, let's say, no? And to avoid to have a neuron very specialized in something, because this something could be noise from the input data. And that's terrible, okay? So there are many cons and pros about deep learning, okay? And of course, this is changing constantly, okay? This is changing constantly, so don't trust anybody which is not involved in artificial intelligence talking about deep learning. And only pay attention to the godfathers of artificial intelligence. And even them can fail, okay? Because the things are changing very quickly. And there are people working in all the fields. So you can, any of the cons at any time can be a pro, okay? So, well, the good thing is that the final sentence, that we are, for the very first time, solving incredible scientific challenges. And in 5-10 years, believe me, I'm sure that a new vaccine is going to maybe, if not totally, in great part, extracted using artificial intelligence and deep neural networks, okay, and using deep reinforcement learning, the same techniques they are using in Dota 2, okay, DeepMind, you see, okay. The good thing is that we have a lot of tools, okay, a lot of tools. I teach Python, Pandas, and these kind of things. We use Google Collaboratory, but my students, they can install Anaconda, Python, and do everything in its own machine. And then we have meta-learning tools. So if you have no idea and you don't want to have idea about this, there are a lot of tools you can use in order to make incredible things without knowing a shit about deep learning. The problem comes when you need to do something different, okay? Without the mathematical background, you are somehow compromised, okay? So if you want to become a good in machine learning, okay, Kaggle is a must, okay? There you can work with Python, where you have notebooks, you can work with Python, and there are competitions, okay? And a lot of tutorials. And there are even people that in their resume, okay, they put their score in Kaggle, okay? How good you are in Kaggle, okay? As a way to see how good you are in machine learning, okay? Famous deep neural network architectures, I would say convolutional neural networks. We don't have time, but they work very well with images, okay? This is the kind of neural network we use with images. We don't use one unique array. We use the image, of course, and we take into account the spatial relationship between the pixels, okay? And this is an example, okay? This is a convolutional neural network. And the last steps we use for the classification, we use the standard neural networks, the fully connected neural networks, okay? So the convolutional layers, okay, they are much more focused on looking for features, okay? So what features is the neural network detecting? You have no idea. Okay, this is the problem. It's a black box. Okay. There are some techniques like this that allows you to pre-visualize somehow what the different layers are paying attention to. Okay. So there are some techniques in order to get you an idea, okay, about what kind of level of information every layer, okay, is considering. And you can see that you start with something complex, which is the image, and you finally finish classifying car, truck, airplane, ship, and horse from complex to simple. Okay, that's clear. Okay, but what a specific neuron does, it's very difficult to know. Okay. Recurrent neural networks are very interesting. In this case, we are not talking about feed forward, so there are backward alimentation, okay? So we have a kind of memory. So this works very well with sequential elements, for example, text. One of the experiments we do is to train a recurrent neural network using Cervantes, our Spanish famous writer, Quixote, and then to start a sentence and let the system to finish the sentence. So what GPT-3 does, okay, but using a recurrent neural network, which is the primitive technique that it is behind GPT-3, if you're interested in looking, which is called transformer, okay? So, okay, this is how it works, the recurrent neural networks. And as you can see, maths. If you want to understand how they work, maths, okay? And deep reinforcement learning, believe me, because I didn't want to put you all the formulas, but it's complex, okay? Deep reinforcement learning, what DeepMind is using is complex. Then we have GANs. I'm sure you have heard about generative adversarial networks, okay? They are incredible. The idea is to have two neural networks, okay, that you train with faces, for example. So now one of them, you add noise, okay? And you use the other one to see if what it is generated, okay, is a face or not. If it is not, okay, you penalize the other neural network, okay? And you say, ah. So it uses this information in order to be able to create better fakes, let's say, of faces, okay? So it's a competition between two neural networks. It was Ian Goodfellow, okay, the man behind this technique. All these images are fake. Nobody, these people does not exist, okay? Autoencoders are very similar, okay? So we compress information and then we decompress information. So working in the latent space, we can do incredible things, okay? So the good thing is, in order to finish, I'm out of time, running out of time, is that if you want to become a specialist, you have to learn maths and to spend a lot of time. If not, there are tools, of course, okay? There are tools and a lot of startups that are going to generate you, how to say it, APIs you can use if you're developing for mobile devices or the web or whatever, okay? Okay, so let me stop sharing the screen. Okay.